Section 9.3, we're going to take a look at something that's called separable equations, or separation of variables. The equations we looked at back when we were dealing with exponential growth and decay, we came up with that formula for exponential growth using separation of variables, or separable equations. Let's take a look at a definition. That a separable equation is a first-order differential equation in which dy over dx can be factored as a function of x times a function of y. For example here, say dy over dx, let's let it equal to g of x times f of y. So it's a function of x times a function of y. To solve, let's let f of y be equal to 1 over h of y. Then dy over dx becomes g of x times 1 over h of y, which is just equal to g of x over h of y. So now we could say h of y dy, multiply both sides by h of y, is equal to g of x dx, multiply both sides by d of x, or dx. Then we integrate. So let's get right to examples. We want to solve dy over dx is equal to xy squared. Now eventually our overall goal is to get an equation of y in terms of x. So I want to get everything that has a y on it to one side and everything with an x on the other side. So I'm going to divide both sides by y squared. So we'll end up with dy over y squared is equal to x times dx. And now we want to take the integral of each side. So actually I'm going to write it this way. I say y to the negative second times dy is going to equal the integral of x dx. So taking the antiderivative here, we're going to get y to the negative first over negative 1. Now I could hold off on all the c's, because if I just have a constant, and I'll write it out so you'll see what I'm talking about. I'll call this one constant. And then we're going to get x squared over 2 plus another constant. Well, now I could just bring all my constants over to one side. So I could rewrite this as negative 1 over y is equal to x squared over 2 plus a third constant. And our constants are just going to be changing throughout. So just know that the c that I'm just going to keep bringing down is going to change when we have to take the different signs for it. But ultimately, at the very end, it's just going to be a constant. So now what I could do is just multiply everything by negative 1. So we're going to get 1 over y is going to equal the opposite of x squared over 2. And then, yeah, technically a negative c, or if it makes more sense, we could just write that this is our fourth constant, just to keep track of them. And then technically, I can multiply both sides by y and then divide by this, or really taking the reciprocal. So y is just going to become 1 over, we could write this as negative 1/2 x squared if you prefer, and then plus, we'll just call it our overall constant. right, so we could say one solution is going to be y equals 1 over negative 1/2 x squared plus c. But since we divided by y, so we need to check y equals 0. Will this work as a solution? All right, so if y is equal to 0, then y prime is going to equal 0. And dy over dx, which is equal to x times y squared, is true. Both sides would equal 0. So y is equal to what we just found here, or another solution would just be y is equal to 0. Yeah, let's take a look at another example. We want to solve dy over dx is equal to x squared over y squared. Then we also want to find the solution. So we'll have a general solution, and then we want to find a solution satisfying initial condition y of 0 is equal to 2. So again, we're going to start by getting the separation of variables. We want to get all the anything that has a y with it on one side. So I'm going to multiply both sides by y squared. So we'll get y squared dy is going to equal x squared dx. We'll take the integral of both sides. So we're going to get y cubed over 3 equals x cubed over 3 plus c. Now at this point, we don't really have to get y by itself just yet because we can check this initial condition here. So using y of 0 is equal to 2. That means x becomes 0 and the y is 2. So we're going to get 2 cubed over 3 is going to equal 0 cubed over 3 plus c. So c is going to equal 8/3. So now we could say we've got y cubed over 3 is equal to x cubed over 3 plus 8/3. Now we'll go ahead and multiply everything by 3. So we'll just get y cubed is equal to x cubed plus 8. Now we'll take the cubed root of both sides. So y is going to equal the cubed root of x cubed plus 8. Now here's a nice way to check. If you were to graph our result, the equation we came up with, the ordered pair 0, 2 should be on that curve. Go through 2 more examples. Let's go ahead and solve du over dt, which is equal to 2t plus secant t squared all over 2u. And we want to find a solution that's going to satisfy u of 0 is equal to -5. Right, so if you notice, everything in the numerator has a t in it, everything in the denominator has a u in it. So again, I'm just going to multiply both sides by 2u. So we'll get a 2u du. It's just going to equal 2t plus secant. We could write it like this, and then have the dt here. And again, we'll take the integral of both sides. So we're just going to get u squared on the left, and we'll get t squared. The antiderivative of secant squared t is what again? Tangent t, and then we'll have our plus c. So at this point now, let's go ahead and figure out what c is. So if u of 0 is equal to -5, that means the u is where we substitute in the -5, and the t's where we substitute in the 0. So we're going to get -5 squared becomes 25, and we'll just get 0 squared plus tangent of 0 plus c. And tangent of 0 is 0, so c is going to equal 25. So now we end up with, going back up to this line right here, we'll have u squared is equal to t squared plus tangent t plus 25. Solving for u now, u is just going to equal, which we could leave it like this, or we could say u is going to equal the square root of t squared plus tangent t plus 25. But to make sure that 0, -5 is on this, or the graph of this equation, we need to make sure that that's going to come out to be a -5, so we have to put the negative out in front. So we say put the negative there to make sure u of 0 turns out to be a -5. All right, we'll do one more example. Again, let's go ahead and find the solution of the differential equation. That satisfies y of 0 is going to equal 0. And our equation, differential equation, is dy over dx is equal to x times e to the y. All right, in this case, we are going to divide both sides by e to the y, so we'll get dy over e to the y is going to equal x dx. We could rewrite this as e to the -y dy is going to equal x dx. We'll take the integral of both sides. Integrating the left side here, remember this is going to become a negative e to the -y is going to equal x squared over 2 plus c. Now at this point we can use that initial condition, y of 0 is equal to 0. So this will give us negative e, can't go wrong here, both y and x are 0, so we get negative e to the 0 is going to equal 0 squared over 2 plus c. So this becomes -1, this will just become 0, so c is -1. So now we say negative e to the -y is equal to x squared over 2 minus 1. We can divide both sides by -1, so we'll get e to the -y is going to equal the opposite of x squared over 2 plus 1. Now to get -y by itself here, we have to get rid of the e, so we want to take the natural log of both sides. Now the reason I'm not including the absolute values is because when this graphs itself, we'll be able to see the domain of it. So now we'll just get -y is equal to the natural log of -x squared plus 1, and then we'll divide both sides by -1. So y is going to equal the opposite of the natural log. We could write this as 1 minus x squared over 2. And again, you can graph this on Desmos or a graphing calculator and then just verify that the ordered pair 0, 0 is on that.